I told you what they are in this cheat sheet. So you can see 10 to the minus 6 is 8.8 dB, 10 to the minus 7, 9.5. You can plug in. Basically, the better we try to make our system, the further away QAM and PAM are from being so-called capacity or highest performance. And this measures a gap in signal power or a gap in noise reduction. Either way, a gap in signal-to-noise ratio improvement. So we're that many dBs away from the best that we could possibly use. If we know the gap for a given type of modulation, and here it is for PAM and QAM, we can almost immediately compute the data rate that we would transmit over the system. Very simple formula. You know the signal-to-noise ratio. You'll know the gap. You may memorize them for a few different commonly used probability of errors. You as an engineer pretty much know how fast you can go on this transmission system. Now there are systems, there are modulation techniques that are better than PAM and QAM. Okay, there are more than one or two dimensions that are used in those transmission techniques. They're multi-dimensional transmission techniques called codes, which have smaller gaps. And there are codes exist that get pretty close to 0 dB on the gap, but they're very complicated to implement. And those are covered actually in the EE379B class, not in the A class. The best codes you're going to see in A are basically these PAM and QAM systems, and we're going to learn how to try to preserve ourselves at this particular level of performance, which is provided by the gap. So let me give you an example or two of how you might use this gap. Okay, so, and I have certainly done this myself in a number of situations, and just trying to give an initial estimate of how fast we could transmit in a given transmission system. Suppose I see a signal-to-noise ratio that's roughly about 13.5 dB, and I want 10 to the minus 6th error rate. Well, I could actually write the formula out as B bar equal 1/2 log base 2 of 1 plus 10 to the 1.35 over 10 to the 0.88. And you will see, indeed, that provides what we already should know, which is 1 bit per dimension. So if I know the symbol rate and I know the signal-to-noise ratio at that particular symbol rate, then I could say the data rate here is going to be R is 1 over T bits per second. Suppose instead somebody comes along and they've measured the channel for the system. Looks like we're getting 24.4 dB of signal-to-noise ratio, a little better looking channel. And we actually want a higher performance or a lower probability of error, 10 to the minus 7th, then my B bar on this channel would be 1/2 log base 2 of 1 plus, and I'll do it a little more quickly this time, 24.4 dB is 2.44 minus 0.95, knowing that the gap for 10 to the minus 7th is 9.5 dB. This works out to be 2.5 bits per dimension. So suppose my symbol rate were 10 megahertz in a QAM system, and I had this signal-to-noise ratio, I could get 25 megabits per second pretty easily using the gap approximation. Suppose my signal-to-noise ratio was a big one. Let's say 44.7 dB. And maybe I have 10 to the minus 6th again. Well, we can reuse the same expression. What will happen is I'll get 10 to the 4.47 minus 0.88. And the B bar in this case works out to be 6. And if it were a QAM design, if it's 6 bits per dimension, that's 12 bits per symbol, because there are 2 dimensions in QAM. So I would have 4,096 QAM. High signal-to-noise ratio, lots of points in the constellation. And I would know that roughly I could have a system that would perform with this, what will probably be a very high data rate. What are the highest number of bits per dimension? Bits per QAM symbol I've seen in use? The actual DSL modems are the highest efficiency systems, and they get all the way up to 15 bits per symbol, or 7.5 bits per dimension, on quite a few of they actually use multiple QAM signals across a 1 megahertz band, and if you have a reasonably short telephone line, which a number of people do, you'll see that system capping out at 15 bits per QAM signal, which is a 30, basically it works out to be about a 32,000 cross constellation that's used in those modems when they can transmit the 15 bits per dimension. Okay, so the gap approximation kind of gets you there quickly. All right, you don't have to go through a lot of analysis to basically know what data rate you might be able to achieve on a channel. Now, on a second pass, after you've been through this and say, okay, it looks good, it's in the right range, then you're going to have to go back to the details. And you'll have to figure out, what does the channel look like exactly? Is it really an additive white Gaussian noise channel? If it's not, am I losing something? Am I gaining something? If it's not an additive white Gaussian noise, if so, how much? And what do I have to pay to get that data rate? And as you increasingly go through the analysis, you'll spend more and more time on it, and you may come up with a design that you like, that you're actually going to go out and implement a modem, sell a product perhaps, that follows this particular design to achieve those speeds. So in order to do that more complete analysis, we're going to have to go back and consider that filter in the channel that I talked about earlier. And to get there, my approach to this is in Chapter 2 on passband analysis. The first thing that we look at for passband signals is we take any signal x of t, and if it can be modeled as a product of some amplitude function a of t and a factor which is essentially a sinusoid, cosine of omega ct, plus some phase which could be time varying, so not necessarily constant. So that's a little different than phasor analysis, which you may have seen in your basic circuit classes. Call this the phase, and we'll call this the amplitude. Any signal that can be written in that form is called a passband signal. It's sometimes also called a carrier modulated waveform. Now, you probably remember from your basic trig classes that when you see cosine of a plus b, you can write cosine of a times cosine of b minus sine of a times sine of b. So we could take a function like this and use that formula, rewrite it as a of t times cosine of omega ct times cosine theta of t minus a of t sine of omega ct sine of theta of t. What I'd like to do is I see this cosine. Oh, that looks a lot like the factor I saw in the QAM modulation functions earlier. And I see sine in the second part. So I'll take everything else and group it together. So let's call a times cosine xi of t. And the I is typically a subscript referring to in-phase component. In-phase being associated with it multiplies cosine. And the a times the sine phi is xq of t. And it's called the quadrature component, quadrature usually meaning it multiplies sine. So we could write this as xi of t times cosine of omega ct minus xq of t times sine of omega ct. And this is called a quadrature decomposition. Why would I want such a thing? Well, because I'm dealing with QAM, which has kind of a cosine dimension for one of the basis functions, and it has a sine dimension for the other basis function. Yes, sir? This is not included. That's what I meant by this line. So delete the cosine omega ct. I carried that out separately. So xi is a times cosine theta only, and xq is a times sine of theta only. Okay, and we could actually think of such a system. You may actually recall that sine actually lags cosine by 90 degrees. So if I wanted to draw a two-dimensional set, it's actually minus sine. That's 90 degrees ahead of cosine if I think of phase angle of omega ct as I move around a circle. Then what happens is I think of the xq component being aligned with minus sine, and the xi component being aligned with cosine. And in fact, I could actually draw a triangle in there where the amplitude function a is the square root of xi squared plus xq squared. And in fact, we could go backwards from this xi and xq, and you would see that a of t is in fact the square root of xi squared plus xq squared. And there's a sine, there's an angle theta here, which is tangent inverse of xq over xi. So we can kind of think of this as some kind of time-varying thing rolling around a circle that's defined by omega ct, some carrier modulated waveform. Kind of nice in this form where we have it decomposed into the two components, which leads me to the definition of a quantity that is heavily used in passband analysis of the type that we're going to pursue, and it's called the baseband equivalent signal. XBB, or baseband of t, is defined as xi of t plus j, which is the square root of minus 1, times xq of t. So you see, for the first time, I've introduced complex numbers or complex functions in the class. And I do this by multiplying the quadrature part by j. So I can think of this as now kind of a complex plane here, with a real part on this axis and an imaginary part on that axis. Baseband equivalent signal. Nowhere does the carrier frequency appear in this baseband analysis. So no carrier. Now think about, why don't I want the carrier around? Well, we saw with all those examples earlier in class today that there are a lot of different types of QAM transmission systems. Okay? And they differ mainly in terms of the descriptions we had, in terms of what carrier frequency. We've got DirecTV using 17 gigahertz. We've got cable modems using maybe just a few megahertz for a carrier frequency, much lower. But basically what we care about is that little frequency band where the signal passes through the channel. I don't really need to know the carrier frequency. All I really need to know is what's happening in and about the carrier frequency. Essentially, if I called that 0, that carrier frequency, and ignored it, re-indexed things, then I'm going to generate a complex description of the channel that replaces the original channel, and it'll work for any carrier frequency. As long as I take the original channel and kind of do something to it, and then start to analyze it as basically centered around some carrier frequency of interest for QAM modulation, I don't need to worry about the carrier frequency anymore. So the first step in that is to kind of forget the carrier frequency in a QAM waveform, because QAM clearly satisfies this form here. Because I had basically a component times a basis function, some phi times cosine omega ct, plus another component times a basis function which had a sine of omega ct in it. So I could forget the cosine and the sine, because that's just moving it around in frequency, and look at essentially what's really going on, okay, on the cosine dimension, which is the in-phase dimension, and the quadrature dimension, which is the complex dimension. So here, in fact, I have a complex waveform that in some way represents the original waveform. Now, I do have to know the carrier frequency to actually know where it is, okay, and what frequency band it actually occupies. But for my analysis, I'm going to try to make this independent of that. I'm going to replace that by a single complex analysis. A third yes, sir. You should probably use your mic again. I'm having trouble hearing also. So.
You're taking care of the carrier frequency in the channel analysis?
Yeah, basically it's going to come. Well, my last topic for today is the so-called passband channels that we might talk about today, or we may get to it on next Tuesday's lecture. So we're going to basically recenter everything that we're dealing with around a carrier frequency. The transmit signal, which is what we're talking about right now, and then the channel, we're going to do the same thing, basically, same thing to find what's going on where we really care about the channel, and we don't care about anything that's way outside the range of transmission. Okay, the third definition here is what's called an analytic equivalent. Now, the analytic equivalent is written x sub capital A of t is the original full waveform x of t plus square root minus 1j times something I call x check of t. And this check, when you see it in this class, is a Hilbert transform. How many of you have actually seen the Hilbert transform in some previous class? This is not a prerequisite for this. I'm going to cover it here. About half of you or so have seen this. It's not particularly difficult, but let me spend a few moments on it. The x check of t, which is called a Hilbert transform, is equal to 1 over pi t convolved with x of t. So it's related to the original function. We convolve it with this kind of weird-looking impulse response, if you will, 1 over pi t. Sometimes I call this script h of t in the notes. So you can think of x of t going into a filter, which is script h, and out comes x check of t. It turns out, and we work out the Fourier transform in the chapter 2, but you can take the Fourier transform of 1 over pi t. If you do it correctly, you'll get minus j times sgn, the signum function, times x of omega. What is a signum function? If the argument is positive, you get plus 1. If the argument is negative, you get minus 1, so it's a sign. If the argument is 0, you get 0. So this Hilbert transform has kind of an interesting property of really not changing the magnitude of the signal at all, but simply for positive frequencies, essentially reducing the phase by 90 degrees, and for negative frequencies, increasing the phase by 90 degrees. So essentially it's kind of rotating the phase of the signals, but not otherwise affecting them, the Hilbert transform. That's kind of a nice property for some things that we'd like to do. And so we have used this x check of t basically in the definition of something we're going to call the analytic equivalent. And this analytic equivalent is going to be useful for converting things that are passband down to baseband. Okay, we're going to find a nice, easy way to take a channel later and figure out what's really going on in an equivalent baseband analysis so that we can take our modulated signal we've defined here and convolve it with some equivalent channel and not have to worry about carrier frequencies anymore. So we're headed that direction. It's real easy for the modulated signal to get this baseband equivalent. For a channel or something else we're dealing with, it may not be so easy to pull out the in-phase and quadrature parts of the channel. So this analytic signal concept will be useful as we proceed to basically be able to convert a channel also into a baseband equivalent and something that we can convolve the input to the channel with to get the output of the channel. So that's where we're headed. Now, what are a few examples of the Hilbert transform? Well, if you think about this interpretation of positive frequencies back 90 degrees, negative frequencies increased 90 degrees in phase, then cosine of omega CT has a Hilbert transform. And I think, well, okay, cosine, what's a Fourier transform of cosine? Well, it's a couple of delta functions, one at positive frequency, one at negative frequency, right? So the positive frequency basically gets multiplied by minus j. The negative frequency gets multiplied by plus j, okay? And I look at that when I'm left, I turn around and do the inverse transform, guess what? I get sine of omega CT. So basically, the Hilbert transform takes a single frequency component and moves it back 90 degrees. That's what's happening. And sine